Okay. Yeah, hi everyone. This is Shishira Reddy. Let's discuss about the topic machine learning models for COVID-19 future forecasting and accuracy perspective. This is an analysis of machine learning techniques and forecasting COVID-19 cases. And these are our teammates. Next slide. Yeah, comes to the introduction. The main objective is forecasting future COVID-19 cases, case numbers using machine learning models to assist in public health planning, and also highlighting the need for accurate forecasting to predict pandemic waves, medical resource allocation, and policy making. And here comes a question: why machine learning? Our traditional epidemiological models often struggle with dynamic and nonlinear data, whereas our machine learning models learn from historical data, adapting to complex and evolving trends. Next slide, please. And source of dataset. Here, data collected from John Hopkins University COVID-19 dataset and World Health Organization and local and international health authorities, and the time period from January 2020 to the present. And thank you. Next slides continued by my friend.
Hello, this is Vaishnavi. When we come to the dataset structure, here we use the format of time series data. Features are the daily cases, recovery rates, death rates, hospitalization, and other related metrics. The third one is the geographic coverage. Here, the global data are data from specific countries or regions. This structure allows tracking and analysis of pandemic trends over time, critical for forecasting and decision making. When we come to the machine learning models explored in this paper are the first one is the linear regression. It predicts the future COVID-19 cases by fitting a straight line to the past data. It works well for the simple patterns but struggles with complex nonlinear trends caused by factors like government interventions or mobility changes. The second one is the random forest. Here it builds multiple decision trees on random data subsets and combines their predictions. This model captures complex nonlinear patterns in features like mobility and government policies, offering more accurate forecasts than linear models. Third one is the support vector machines (SVM) are used to classify pandemic phases such as high risk versus low risk periods. SVM detects patterns like case spikes and help categorize risk level based on distinct boundaries in the data. And the last one is the long short term memory, that's LSTM, a type of recurrent network. It excels at time series forecasting by storing historical information. It effectively recognizes long term trends influenced by factors such as lockdowns, making it ideal for predicting COVID 19 cases in complex situations. And the next will be continued by my teammate.
Hello everyone, this is Ramya. And coming to the research process, this process mainly includes 5 steps. In this, the first one is about the data collection. The researchers gathers the data from multiple reliable resources such as the Johns Hopkins University COVID-19 dataset and WHO reports and Google mobility data. This allowed them to capture both the case numbers and relevant factors such as human mobility trends which influence the transmission rates. Next, coming to the data pre-processing. Before feeding the data into the machine learning models, the researchers performed extensive cleaning and normalization to handle missing values. And also they remove the duplicates and ensures that data was in the consistent format. They also remove the outliers such as the anomalous high case swings that might skew the model's predictions. Coming to the model training, the clean dataset was divided into the training and testing datasets, with the training set being used to take the machine learning models to recognize the patterns in the data. Each models like linear regression, random forest, SVM, and LSTM was trained on a historical case numbers and mobility trends to make accurate forecasts. Coming to the model evaluation, after training, the models were evaluated using the cross validation techniques, which involves splitting the dataset into multiple folds and testing the model on unseen data in each fold. This ensured that the models generalized well to the new data, reducing the chances of overfitting. Coming to the hyperparameter tuning, to optimize performance, researchers adjusted the model's hyperparameters, the settings that controls how the models learn. Example, the number of trees in the random forest or learning rate in the LSTM. By by tuning these parameters, the model's accuracy was significantly improved, ensuring better predictions for future COVID-19 case numbers. Next slide, please. Coming to the model performance metrics, we have mainly two matrices like evaluation metrics and model comparison. In evaluation metrics, we have the MAE, mean absolute error, which can measure the average absolute difference between predicted and actual values. Next, coming to the root mean squared error, which indicates the square root of the average squared differences. Next, R squared, which can reflect how well the model explains the variance in the data. Coming to the model comparison, LSTM achieves the lowest root mean squared error, making it the most accurate for time series forecasting. Random forest performed better than linear regression due to its ability to capture non-linear relationship. Thank you. And the next slides will be continued by my friend Fanindra.
Okay, thank you, Ramya. I'll be taking through the research results for the visualizations. In the first visualization, we have compared the actual versus predicted COVID-19 cases. So from this, key insight is the LSTM, long short term memory follows the actual trend compared to the linear regression, whereas the linear regression is on lags. And we have the second visualization chart. It is the bar chart of metrics MAE and RMSE, which are MAE means mean absolute error, and RSME is the root mean square errors. So in this, the key insights are long short term memory and the random forest outperform similar models. And we can show you in the code too. This is the code that we have run, and we got the results. These are the snapshot of the results, which I can show you through the code. This is the code that we have used for the comparison of actual and the predicted COVID-19 cases. We have taken an average range of dates for 1 year and taken given the random cases for throughout that year, and we have plotted that graphs using the algorithms LSTM and the linear regressions, which we can see the red is the linear regression that has there is no lags, but when compared to these are the graphs, and we have in the second one is about the bar graphs of errors, where we can see in LSTM we have less number of errors when compared to the random forest models and the linear regression models. We'll go back to the PPT. Those snapshots we have pasted over here, and challenges and limitations will be taken by one of our friends.
Hello everyone. So when it comes to challenges and limitations, challenges we have data availability, challenging dynamics, and outfitting. When it comes to data availability, inconsistent reporting of cases and deaths across different regions leads to noisy data. Challenging dynamics, new COVID-19 variants and evolving in interventions make it difficult for the models to stay relevant. Overfitting, some models like deep learning risk overfitting in if not tuned correctly. So the limitations of the study are model trained on early COVID-19 data may not fully capture and behave for new variants. Not all data sets were available during early stages of the pandemic. Next slide, please. So when it comes to the conclusion, the application of machine learning in forecasting COVID-19 trends highlights the potential of these technologies to revolutionize public health strategies by leveraging large data sets and sophisticated algorithms like models like LSTM and random forest enable more accurate predictions, helping to anticipate future outbreaks and mitigate their impact. However, to fully realize the potential of these tools, continuous updates and integration of new variables such as emerging virus variants, vaccination rates, and real time availability data are very crucial. Moving forward, the synergy between machine learning and epidemiology can play a key role in managing not only COVID-19 but also future public health emergencies. So the next slides will be continued by my teammate.
Hello everyone. Our project has a future scope in real-time forecasting and incorporating more features. And one more is cross-relational forecasting, which extends models to forecast for specific regions or countries, taking local data and healthcare data capacity into the account. One more. Next slide, please. We done this project by taking the references from the machine learning model from COVID-19 future forecasting. And one more is data is taken by John Hopkins University, WHO, Google Mobility Reports. And we use tools like Python, Pandas, and MATLAB. Yeah, done. Thank you.